Hello. Hello, good morning to all. Yes, can you hear me? Ankita, how are you? Okay, right. Okay, right. So let us start our lecture. Again, try to join as early as possible. Now I will to share my screen. Okay, can you see my screen? Right?
Yes.
Okay, so we are discussing about the NMR, nuclear magnetic resonance. Once again, good morning to all, and we are going to discuss about the NMR. In the previous lecture, we have seen some basic concept in the NMR, and there we have seen the equivalent proton, number of signals, chemical shift, coupling constant, what is the TMS, the splitting of the signal, magnetic and non-magnetic nuclei, then shielding and de-shielding effect, and where is the position of the signal. So all this point we have seen, and we have also discussed some numerical problems on this one. We are discussing about the site of unsaturation. Site of unsaturation. So I will take this pointer, site of unsaturation. Site of unsaturation. So when this point is compulsory in the UV, IR and NMR. UV, IR and NMR. So you should know in this UV, IR and NMR how to find out the site of unsaturation, right? Site of unsaturation means how many multiple bonds are present. How many multiple bonds are present in that one. So if you have given any molecular formula and it is asked to find out the structure of that compound, then you should know that is site of unsaturation. Site of unsaturation. So in site of unsaturation, you find out how many multiple bonds are present. So I will take some numericals from there. Of course, a compulsory question they will ask on this one. So this point also you will find in the last topic of the spectroscopy on the page number 145. So I will take only few representative, and if you want to ask any other question, you may. Suppose in one case, suppose it contains only, that is the sometimes it contains oxygen and sulfur. So you have to neglect this sulfur and oxygen, and you have to find out the site of unsaturation. For example, C10, H16 and O. So I told you that for this one, we have to neglect this oxygen and we have to write down corresponding molecular formula C10H16. Further, you have to convert into corresponding, that is a saturated alkane. Means you have to put in the formula, that is CN S2N plus 2. Here N is equal to 2, means double octane plus 2. Double octane 20. 20 plus 2, 22. So C10H22. Then we have to subtract this molecule formula from C10H16. So it will, you'll find that here you are having a 4 plus 2 means 6 hydrogen, right? Then you have to divide by 2. So it contains 3 side of unsaturation. It contains 3 side of unsaturation, right? Number 2 example. So remember, when it contains oxygen and sulfur, you have to remove that oxygen and sulfur, you have to convert into corresponding hydrocarbon, and then you have to see the corresponding molecule formula into corresponding alkane. Means you have to put in the formula, that is the CnS2n plus 2, where n is the number of a carbon atom. So you get C10H22, and then you have to subtract this molecule formula by this one. So whatever number you get, you have to just divide by 2, because for the formation of the bond you have to remove the 2 hydrogen. Okay, so you get 3 answer. It contains 3 sides of unsaturation. Okay, next one, suppose if it contains number 2, right? If it contains halogen, right? So if it contains halogen, for example, fluorine, chlorine, bromine, iodine, and it contains either fluorine, chlorine, bromine, or iodine, then in this case, what you do, we have to replace this fluorine and chlorine by hydrogen. You have to replace by hydrogen. So you have to replace by hydrogen all this group. Okay, for example, suppose you are having a molecule formula C3H3 and Cl5, right? So again, same thing, corresponding molecule formula, when there is a halogen, you have to replace by corresponding, that is halogen by hydrogen. So it becomes C3H. If you replace Cl5 by H, so this 5 and 3 means 8. So it will convert into 8, right? Then you have to convert into corresponding alkane. Alkane means CnS2n plus 2. So what is the formula? C3, yes, C3 H8, C3H8, right? C3H8, right? Then you have to subtract this one. And you get, that is the 0 hydrogen atom. So as it contains 0 hydrogen atom, means here there's no need to divide by 2, because it is 0. Means here the site of unsaturation is a 0. The site of unsaturation is a 0. Right? It do not contains any double bond or a ring. Okay. So you have seen the second example. Next example, suppose if it contains nitrogen, so if it contains nitrogen, then we have to replace nitrogen by CH, right? You have to replace by nitrogen by CH. For example, C3, right? Then H5 and ON, C3H5ON, right? So this C3H5ON, it corresponds to, now look here, first formula tells us that if oxygen is there, you have to remove that oxygen, means you have to omit that oxygen. Then there is nitrogen. If nitrogen is there, you have to replace nitrogen by CH, right? You have to replace nitrogen by CH. So the formula becomes C4, because this 3 and this 1 means C4, H5 and this H means H6, C4, H6, right? So this oxygen we have removed, right? And this nitrogen is replaced by the CH. So the corresponding formula becomes C4H6. We have to convert into corresponding alkane, CnS2n plus 2. So it becomes C4 8 H10, right? C4H10. Then you have to subtract C4H10 This C4H6 from
The
C4,
H
it is a 2 hydrogen, right? You have to divide by S10. Yes, it is S10, not 8, it is a S10. C4AH10, right? It is a C4AH10. So here is H10, right? So 10 minus 6 is equal to 4, right? 10 minus 6 is equal to 4. So here you are having the 4 hydrogen, and 4 hydrogen divided by 2 is equal to, that is the 2, means it contains 2 site of unsaturation. It contains 2 site of unsaturation. So in this way we have seen only 3 possibility. Either it contains oxygen sulfur, or either it contains hydrogen, or it may contain nitrogen. So this point is very important. You must know how to find out site of unsaturation. Of course, in exam also they will ask how many unsaturation or site of unsaturation is present in a so and so molecule, right? So I think there is no need to take the practice on this molecule, on this one. So you can find out the site of unsaturation, right? And if you want to take any one example, right, you may tell me page number, question number, I will take that one. Otherwise, you tell me my formula, I will write and I will take it, sir. That is the corresponding site of unsaturation. Yes, bolo. Any problem? No problem. No problem. प्रीतम, कुछ पूछना चाहते हो? Yes. प्रीतम वहां पे, आप वहां पे हो? यस प्रीतम, आवाज आ रहा है आपको? Okay, so I think there is no need to take more problems on this NMR. So remember, in NMR, whatever you have taken, if you know that one, and the side of unsaturation, you can solve any question in the NMR. You can solve any question in the NMR. After completing this UV and IR, I will take some combined problem and objective on that one. Means when your concepts are clear, then you can solve that type of questions. Okay, so let us see the next point we'll take, that is the uh, uh, we have taken the NMR, right? Now we'll take, that is UV spectroscopy. UV spectroscopy. Here we have to take, that is the UV spectroscopy. You know what is meant by UV spectroscopy. So this is the instrument which is useful to find out the structure of organic compound. What is use of UV? What it gives information? It gives information about the dyne system. Dyne system.
double
Double bond means when the 2 pi bonds are in the conjugation. I say in the conjugation, then you can detect in the UV. So 2 pi bonds are in the conjugation. At least 2 pi bonds are in the conjugation. There is a 1 pi bond and there is a second pi bond. If they are in the conjugation, then we can check, we can detect in the UV spectroscopy. Right now, this UV also gives information about this called either dyne, diene. Di means 2, in means alkene, diene, and other is enone. So there is the presence of a CO and 1 carbon double bond in the conjugation. So this carbon is called as alpha and this carbon is called as a beta. So this system is called as alpha beta unsaturated carbonyl compound. Carbonyl compound, right? Carbonyl compound. This carbonyl compound, generally it is aldehyde or ketone. Aldehyde or ketone. aldehyde or a ketone, right? So we detect this is also called as enone. This is also called as a enone. So what is the use of UV spectroscopy? It is useful to find out the presence of the diene, means whether the structure contains either two pi bonds are in the conjugation or not, or one pi bond, carbon carbon double bond, and one CO group, they are in the conjugation or not, right? So this is the use of a spectroscopy. Now here we'll see what is the range for this UV. So in UV you are using ultraviolet radiation, ultraviolet radiation. So if you see the range for this UV spectroscopy, so here it is starting from 100 nanometer, 100 nanometer to 200 nanometer, and 200 nanometer to 400 nanometer, 400 nanometer, right? Here, this 100 nanometer to 200 nanometer, it is not so useful as an organic point of view. As an organic point of view, it is not so useful. We are interested only in 200 to 400 nanometer. It is called as ultraviolet radiation. This ultraviolet radiation. So it is called as ultraviolet radiation. Right? So you know the electromagnetic spectrum. So generally, this UV starts from 100 to 400 nanometer, 100 to 400 nanometer. In that one again, the 100 to 200 nanometer, right? So this is not so important. We are interested only in the 200 to 400 nanometer, right? So this about the UV spectroscopy, right? Now here this 100 to 200 nanometer generally we are using in the vacuum ultraviolet spectroscopy, vacuum ultraviolet spectroscopy. And here what happened, there is a compound, right? Orange compound, we pass electromagnetic radiation, that is UV light. Then this compound will pass this ultraviolet radiation. Some of the light get absorbed, right? And some light get out of from this one. And here we detect the light which get reflected by using the Lambert's Beer law. Lambert's Beer law, and what much amount of the light get absorbed. So here A absorbance is equal to epsilon into C into L, where this is the extension coefficient. This is the extension coefficient. C is the concentration of that solution, and this L is the length of that cell, and A is the absorbance. So here we find out the absorbance in the UV. So here what you do, we plot a graph, and we plot a graph where you take ultraviolet radiation. Here it range maybe from, that is a 200, or we can say 220, then 240, right? So up to, that is a 300 to 400, right? 300 to, or maybe 400. Okay, or instrument ourselves we have the 1000 capacity. So here is absorbance, and we draw a plot, and here we get a spectra like this one, and this is the maximum. It is called as a lambda max, right? We have to find out the lambda max. We have to find out the lambda max in the UV spectroscopy. So we detect the lambda max here. So here we should know Lambert's their law. They may sometimes they may also ask the absorbance is directly proportional to concentration of the solution, length of the cell, right? Like this one, they may ask like this one. Okay, so which radiation we are used? We are using ultraviolet radiation. What is the range? Range is 200 to 400 nanometer. What is the use? It is useful to find out the presence of a diene and immune system. Then it is alias or a ketone. Just 100 and 200, it is not useful as an organic point of view. So we use in the alpha, and that's the vacuum spectrophotometer, right? So this is in general about the UV. So we have seen that is the UV spectroscopy. Here again in this one, the sample we are using in sometimes they may when you see the instrumentation of this UV spectroscopy. So generally they may also ask what type of source we use, what type of source we use. So in UV, generally we use either a deuterium or a hydrogen lamp, hydrogen discharge lamp, whose which can emit the wavelength 180 to 400 nanometer, 180 to 400 nanometer, deuterium or a hydrogen lamp. Sometimes also we can use the tungsten filament. So here it can omit, or it can it can discharge the wavelength near about more than 357 nanometer. So generally we use the deuterium, hydrogen or tungsten filament. Okay, and the container that we are using for this one container container we use generally. So they are made up of quartz crystal, or they may be of a pure silica, pure silica. So sometimes they may ask that what type of container we use in the UV spectroscopy, right? So we are use a quartz crystal, and we can use also silica gel. Here, it should be transparent, and generally the path length of that cell, means the length of this one, generally it is a 1 centimeter. One 1 centimeter path length, right? And here in this case, we are not using glass cell. We are not using the glass cell, right? In this UV spectroscopy, we are not using the glass cell. So again they may ask why we don't use the glass cell in the UV spectroscopy, because the glass cell, if you see it, if you take that one, we get a spectra at a 300 nanometer, is in the range 200 to 400. That's why we are not using the, that is the glass cell. We are using the quartz crystal or the pure silicon, right? But we are not using the glass cell. So sometimes they may ask what type of, why you are not using the glass cell? Why? Because they absorb at a 300 nanometer. And here also, if you use the sample that we have used in this UV, it's a very uh, 2 milligram of sample we have to take. So we can use near about 100 milligram, 100 milligram mg, 100 milligram, 100 milligram, right? Sample we can use, and the solvent, uh, or you can use from 1 milligram to 10 milligram, right? 1 milligram to 10 milligram. This sample we can use very less amount of the sample we have to use, right? Sometimes also they may ask for what type of solvent we use in the UV. So generally, the solvent that which cannot absorb this UV radiation we have to use, right? So here, in this one, we can use, that is a non-absorbing solvent like a cyclohexane solvent, that is a cyclohexane solvent, that is a cyclohexane. There is cyclohexane. Cyclohexane contains carbon-carbon single bond, so there is no double bond, there is no CO group. So cyclohexane we can use. We can use a 1,4 dioxane, 1,4 dioxane, 1,4 dioxane, or we can use a 95% ethyl alcohol, 95% ETOH, ethyl alcohol. But we are not using absolute alcohol, right? So they may also ask why we are not using the absolute alcohol. absolute ethyl alcohol, absolute ethyl alcohol, right? So, so why you are not using the absolute ethyl alcohol? The answer is that this absolute ethyl alcohol we are not using because it contains some traces of benzene, and you know the benzene contains a pi bond, right? So you are getting a signal at 255 nanometer, right? 255 nanometer. So we are not using a such type of that is the uh, solvent, right? So generally use that is a cyclohexane, or we can use a 95% alcohol or 1,4 dioxide. So sometimes they may also ask us such type of the question. Now here I have told you that we cannot use 100 to 200 nanometer, right? 100 to 200 nanometer UV radiation for the this purpose. Why? Because in this case, here if you use this one, then it may generally it is useful to find out the presence of that is a carbon-carbon single bond. Sometimes also they also absorb this radiation also absorb air, moisture, right? And that's why we are not using this one. So they are not useful for the detection of the carbon-carbon double bond. So it is useful for the finding out the bond energy, right? So it is called as a vacuum ultraviolet. We have just also the Lambert's Beer law. So I think this is your Lambert's Beer law, and it is your you should know it's the equation, right? Then if you see this ultraviolet, it undergo electronic excitation, electronic excitation, electronic excitation. So the Argonic compound contains three bonds. Either it contains sigma bond, it contains pi electrons, or it contains non-bonding electrons. Right. So here, what happens? This energy contains either it contains electronic. It may contain a vibrational, or it may contain that is the rotational. Rotational, electronic, vibrational, or a rotational. So this E, we can say E is equal to either E plus either V or either rotational R, right? So what happens? The any orange compounds either contains a sigma bond. For example, if I take simple example CS3 C double bond OH, that is a ketone, right? Or we can take alpha beta unsaturated compound RCH double bond C double bond CH double bond OH, right? So either it may contain such type of alpha beta unsaturated compound. So here you find that either it contains a sigma bond, this is a sigma bond, this is a sigma bond, they all contain sigma bond, it contains pi bond, so there are the two pi bond, and it may also contains a lone pair, means a non-bonding electron. So these three types contains in this one, right? So sigma bond, pi bond, and N non-bonding electrons are present. So they may also ask that how it undergo electronic excitation. Electronic excitation. So which excitation takes place in the ultraviolet radiation. Now UV is more energetic. It has the more energy. So as it has the more energy, the electrons present in the bond they undergo electronic excitation. Electronic excitation. So it have four type of excitation. It have the four type of excitation. So number one, sigma to sigma star, sigma to sigma star transition. Number two, pi to pi star, pi to pi star transition. Always they ask one question on here, pi to pi star. Number three, N2 sigma star, and number 4 N2 pi star transition. And so these are the 4 type of transition takes place. So here sigma to sigma star, if I write there here uh, the diagram, here is the energy, here is the energy, and these are the suppose it is a sigma sigma electron. Suppose it is a pi electron, it is a pi, then it is a non-bonding electron, then pi star corresponding antibonding orbital pi star, and then sigma star, right? Then sigma star, right? So sigma to sigma star means when the system contains sigma bond, then one of the electron when shifted from sigma to sigma star, it is called as a sigma to sigma star transition. For example, suppose if you take alkane, right? So it can be sigma bond, right? It can be sigma bond, or you can take any compound which contains sigma bond. Sigma bond here, it one sigma bond means there are the two electron. There are the two electron. Here is a one electron, and other is a this is the second electron. So what happened in the sigma to sigma star transition? One of the sigma bond is shifted to the sigma star, right? So here is the carbon, right? Here is the carbon, right? And one of the electron from the sigma bond is shifted to the sigma star. So here one of the electron is shifted here. Actually, these are in the ground state, but here one of the electron actually shift to the sigma star, sigma star, sigma to sigma star, So it undergoes sigma to sigma star, right? And so which molecules they undergo sigma to sigma star? Of course, all contains which contains sigma bond is they undergo sigma to sigma star. Example, simple example, hydrocarbon, right? Hydrocarbon. Example, alkene, alkyne. So which contains sigma bond? Even the above example contains this sigma bond, Cs sigma bond, Cc sigma bond, CO. There are two pi bond, one pi bond and one sigma bond. So all that they can show the sigma bond. So in this case, what happened? One of the electron from the sigma it is shifted to the sigma star. So it is called as a sigma to sigma star transition. Sigma to sigma star transition. So most all they undergo sigma to sigma star transition. The next one is the pi to pi star. Pi to pi star means the pi bond which have the pi bond, right? So there is the one number two, right? So the compound which contains a pi bond. For example, here is the carbon, here is the carbon carbon double bond, right? Here is the carbon carbon double bond. One pi bond means two electrons. So I can write one pi bond means two electrons. So it contains two electrons. So I can write suppose if I write here two electrons in the ground state, here is a one and here is a two. It is a pi bond. So here it undergo pi to pi star transition, right? Pi to pi star transition. How it undergo pi to pi star transition? Here is a sigma bond, right? One of the electron from this one is shifted to the pi star. So this will shift to the pi star, pi star. So it is a pi bond and it is shifted to the pi star. So here is a pi and this is shifted to the pi star. So which how the pi bond any compound which contains pi bond, that is a carbon carbon double bond, that is alkene. Alkene contains a carbon carbon double bond. Alkyne contains a carbon carbon double bond, right? So anything which have the pi bond, it undergo pi to pi star transition. Even to carbonyl group, that is the aldehydes ketones also contains a pi bond. Here one of the here is a pi bond, so it also undergo pi to pi star. Aldehydes ketones esters they undergo pi to pi star transition. So what is the pi to pi star transition? Pi to pi star transition means one of the electron from the pi bond is shifted towards the pi star. It's called as pi to pi star transition. Pi to pi star transition, right? So we should know which compound contains some pi bond, so they undergo pi to pi star transition. Next one, Here, next is N2 sigma star, which contains non-bonded electron. Generally, it contains this hetero element like oxygen, hetero element like oxygen. Oxygen contains lone pair, right? So it undergo pi to pi star, into pi star transition, right? So let us see how it undergo into pi star transition. Number three. In number three, suppose if you take a simple example, that is a CH3, and here is O, and here is H. Now it contains here the two lone pair, right? It contains two lone pair. These are the non-bonding orbital, right? These are the non-bonding orbital, right? So one of the lone pair when shifted, right? One of the lone pair when shifted to the sigma star, that is called as a sigma to sigma star transition. It is called as that is a sigma to into sigma star transition, into sigma star transition, right? So we can write here that is the CH3. In particular, just I have written here CH3. Here is the oxygen, here is the H, 1, 2, here is the 3, and one of the hydrogen will shifted to the here is a sigma. Here is a sigma, right? So here you are shifting to the sigma star. You are shifting towards the sigma star. So non-bonding orbital will shifted to the sigma star. So it is the sigma to N to sigma star. Example alcohol, ether. So this show the sigma, this type of transition. As organic point of view, the second is important, right? As organic point of view, the second is important, right? As organic point of view, the second is important. As organic point of view, the second is important, right? As organic point of view, the second is important. That is the pi to pi star, right? Pi to pi star. Now we have seen N2 sigma star. So one of the electron from N is shifted to sigma star is called as N2 sigma star transition. N2 sigma star transition. Example which contains lone pair. Example alcohol, right? Example alcohol, right? Example ether, right? So they are not so important. This two is important, right? Number three, that is a fourth. Fourth is the N2 pi star, right? N2 pi star. So one of the lone pair when shifted towards the pi, then it is called as the N2 pi star transition. Example, at CS3, C double bond O and H is aldehyde. Here it contains two lone pair, one and two lone pair, and it contains two lone pair. So when one of the lone pair is shifted towards the pi star, so it is called as sigma to pi star transition. Pi star transition. So you are getting a CS3. Here is C, here is the H, here is the double bond O, right? One lone pair, second lone pair, and here one lone pair is shifted here, right? So you are having a pi star,
Fine.
pi star. Okay, pi. Yeah, sigma to pi star. Example, aldehydes, ketones. It must contains pi bond and it must contains one hetero element. So it is called as this one. So in exam, what they may ask, they will give the compounds, name of the compounds, and they'll ask out of following which undergo sigma to sigma star transition, pi to pi star transition, n to sigma star transition, sigma to pi star transition, and here is your sigma to pi star transition, right? Here is the not sigma, it is n, na, n, sorry, n, it is n, not sigma, it is n to sigma star, it is the n to sigma star. So here the last we have to write n to pi star. Here is the n and here is the pi, n to pi star transition, n to pi star transition, right? So in exam, what they may ask out of this four transition which require more energy, out of following which require more energy, right? So if you see here, sigma to sigma star require more energy, right? So here you have to remember this data, right? So sigma to sigma star, it requires the more energy. So sigma to sigma star require more energy. Then you have to n to sigma star, n to sigma star, then pi to pi star, pi to pi star, and then n to pi star, n to pi star. Right? So sometimes they'll ask, write down the sequence in the increasing or decreasing order of their energy. So here, this sigma to sigma star require more energy than n to sigma star. You look here. Here, in the first two cases, the electrons are shifting towards the sigma star. In the second cases, the electrons are shifting towards the pi star. Right. So you have to again you see that the second one is the n to sigma star and n to pi star. Right. So in this way, you can remember, yeah, sigma to sigma star, right? N to sigma star, then pi to pi star, and n to pi star. Okay, so here in this way we can write their energy, right? So this is about your energy. Now, if you take the another example, right? For example, if you are having a such type of compound, you can tell me CS3, C double bond O, and there is a CS3, right? Now it undergo pi to pi star transition, right? It is very strong pi to pi star transition, and you are getting a corresponding CS3 C. Here is the CH3 pi to pi star transition. Here you are having a corresponding a pi to pi star transition. Here is one of the electron from this one. It shifted towards pi. So oxygen, it have two lone pair, and one of the electron is shifted to pi star, right? And it absorbs at 190 nanometer. Means look again, this spectra is below 200. Means even though it contains pi to pi star, it get absorbed below 200. And actually our scale is from 100 to 200, 100 to 200, and 200 to 400, and 400 to 800 is visible. It is the visible, right? So here it absorbs at 190 nanometer, right? This strong, right? And at the same time, it also undergo N to pi star transition. Means one of the electron from this oxygen is shifted towards the pi star, and here CH3 C double bond O. Here is a CH3 one pair second, and this will shifted towards the pi star, and it appear at 280 nanometer, 280 nanometer. But here the extension coefficient is a 15, and the extension coefficient is a 100. And even though it appears in the one in 280, means here the band due to N2 pi star appear in the ultraviolet region, right? N2 pi star, even though the two pi bonds are not in the conjugation. Sometimes they may also ask why you get, right, acetone a band at 280 in the ultraviolet spectroscopy. Generally, if two pi bonds are in the conjugation, or one pi bond and one CO group in the conjugation, then it is a UV active. Means you are getting the signal in the 200 to 400 nanometer. But here, this acetone, even though it do not contains pi bond, then also you are getting a signal at 280, and at 280. So what is reason? The reason is that it undergo N2 pi star transition. So you have to tell that it undergo N2 pi star transition, right? So that's why you are getting that type of the signal, right? So this is about the extension coefficient. Some basic terms you should know. That is the chromophore. Sometimes they may ask definition. What is meant by chromophore? Chromophore is a function group which have ability to that is absorb UV light is called as a chromophore. Any function group which absorb UV light means 200 to 400 nanometer. It is called as a chromophore. Example here, they will also ask the examples of this one. Here is NO2 nitro group. Look here, nitro compound. They look color to our eyes. Why? Because they absorb in the UV visible range. Nitro group, the N double bond O, right? Then N double bond N, then CO group, just now we have seen CO group carbonyl compound, then carbon carbon double bond, carbon carbon double bond, right? Then a carbon sulfur double bond, carbon sulfur double bond. So all these are the chromophore. Chromo means color, phore means bearing, color bearing compound, or color absorbing compound, right? So which have the color, they are called as a chromophore. Example this one. Then number two, exochrome. 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 Exochrome is color increaser, right? Color increaser. It increases the color. So these are the function group. These are the function group which do not absorb in the UV spectrum. But when they attach to the chromophore, then the lambda max or the wavelength get increased. It is called as a exochrome. Example, suppose this is your benzene, right? Here is the pi bond, pi bond, pi bond. This benzene, it appear at 255 nanometer. 255 nanometer means it is in the range of a UV light, right? So it is a chromophore, right? But if you take example, that is OH phenol, this OH do not absorb this UV light, right? Means it is not a chromophore. But suppose if you attach to the chromophore, here is the pi bond, here is the pi bond, here is the pi bond. If you attach to the chromophore OH, right, then the lambda max get increased. The lambda max get increased at 270 nanometer. 270 nanometer means there is increase in the lambda max. So the group when attached to the chromophore, when lambda max get increased, that functional group is called as a oxochrome. It is called as a oxochrome. Example, another example, OCH3 methoxy group. Here, if you put the methoxy group, it is called as anisole. It is called as a anisole, and it appear at 269 nanometer, means more than 255. So they are called as a, that is exochrome. So we have seen the concept of that is a chromophore and exochrome. Next point, they may ask bathochromic shift. What is the mean by bathochromic shift? Bathochromic shift. Sometimes they may also say that a red shift, right? Bathochromic shift is also called as a red shift, right? So what is red shift or bathochromic shift? For example, right? So here you are having a such type of example. Here is a pi bond, pi bond, pi bond. Here is a N double bond O and O minus and N positive. It is called as a nitrobenzene, and here is the OH, right? That's the OH. So lambda max here in this case is equal to 255 nanometer. But suppose if you carry out if you put this compound in the alkali, right, and if you take its spectra, then you see that there is an increase in the lambda max. There is an increase in the lambda max. So in the alkali, why the lambda max get increased? They may also ask, or what is the name of that shift? It is called as a bathochromic shift. So what is the bathochromic shift? Here, in the presence of alkali, this sigma bond shift on the oxygen, there is the formation of O negative, right? And here As the formation of O negative, this O negative they can be involved into delocalization as compared to phenol. So the length of a conjugation get increased. This pi bond will shift here O negative, N positive, right? Already N positive, right? Then this will shift here, right? Then the formation of double bond. Carbon becomes positive. This will shift here, formation of double bond, and this negative will shift here. So they are involved into delocalization. So here, in this case, the extension coefficient was only 900, but here the extension coefficient is a 15,000, 15,000, and the lambda max will increase from 255 to 265, means there is increase in the lambda max. So it is called as a bathochromic shift. It is called as a bathochromic shift, right? So when there is increase in the lambda max of a molecule is called as a bathochromic shift. It is also called as a red shift. Then one hypochromic shift, and next one is the hypochromic shift, right? So hypochromic shift, hypochromic shift is also called as a blue shift, right? Blue shift. So here what happened, there is a decrease in the lambda max. There is a decrease in the lambda max. For example, these are aniline, right? So from here we can say that when there is a length of a conjugation get increased, the more the conjugation, more is the lambda max. More the conjugation, more is the lambda max. In the previous example, you will see that the length of conjugation get increased, right? Why? Because this O negative can undergo delocalization very easily as compared to phenol. So length of conjugation get increased, right? Now next example, here we are having aniline NH2. NH2 contains lone pair. Now this when you carry out its lambda max in the HCl, here is the lambda max. Lambda max is equal to 230 nanometer, right? And when you take in the spectra in the presence of HCl acid, then the lambda max get decreased. So decrease in the lambda max is called as a red shift or blue shift.
Blue shift.
Right, it is called as a blue shift, right? So it is called as a blue shift. Why blue shift? Because here NH2 becomes NH3 positive. Now there was a lone pair, so this pi bond may involve into delocalization. So here we can say that this pi bond will shift here, this pi bond will shift here, and this pi bond will shift here. As this is shift here, the lone pair they are involved into delocalization, right? They are involved into delocalization, right? So here, as in this case, the lone pair in the aniline they are involved into delocalization. The length of conjugation is increased, but in this one, when you carry out its spectra in the presence of HCl, there is a formation of salt. Now here there is no lone pair, no lone pair, no delocalization, no delocalization. The length of conjugation get decrease is called as a blue shift. Is called as a blue shift. So here, yes, huh. Suppose you are having a spectra like this one. You are having a spectra like this one, right? So in the red shift, what happen? This is your lambda max. This is your lambda max, right? So in the red shift, what happen? The spectra get shifted towards the right side, right? The spectra get shifted towards the right side is called as a red shift, right? So here you are having a lambda max, right? Lambda max, and in the blue shift, what happen? The spectra gets shifted towards the left side, right? It gets shifted towards the left side. So here is a lambda max. So lambda max. So it is called as a red shift. It is called as a blue shift. Understand what is by a red shift and a blue shift, right? Now next two are there. So uh, hypochromic hyperchromic and hypochromic. Hyper hyperchromic shift and hypo HYPO hypochromic shift. Hyper means more. Hyper means more, and hypo means lower. Hypo means lower. Hyper means more. So here what happen? The lambda max get appear here, right? Appear here. In the hyperchromic, the intensity, the height of that absorption get increased, means it will appear at the same lambda max, but here the intensity is more. The intensity is more. Here the intensity of this lambda max is more, right? So you are having a such type of that is the spectra. Here this is increase in the intensity, right? So the absorption A get increased, the height, the amplitude get increased. It is called as a hyper. Hyper means more. Hyperchromic shift. And in the hypo, there is a decrease in the intensity. There is a decrease in the intensity. So in this one, here the intensity get a decrease, right? Intensity get a decrease, right? So this is the, it is called as a, that is a, this is called as a hypo, right? Hypo. So in, I have shown all this shift in one diagram. Okay, so these are the some basic concept one should know, right, in the UV spectroscopy. And then after this one also you have to show, you should know some basic concept, that is what is the dyne, exocyclic double bond, endocyclic double bond, and Woodward's and Pfizer rule. What is the effect of conjugation? And then we can solve any questions on this one. So here I am taking only 2 points selectively, which are important, right? And on that one, they may also ask a objective question, right? Any doubt you can ask. इसके ऊपर कोई आपको doubt है, यदि आपको कुछ पूछना है तो आप पूछ सकते हो. If you want to ask anything, you may ask. Yes. Any question? Prachi Sabre, any question? Yes. No. थोड़ा घर पे पढ़ाई करो, and then try to ask us some questions. Pritam. Yes. Are you there, Pritam? Pritam, आप वहाँ पे हो क्या? Okay. Ankita, are you getting?
Yes, sir.
हाँ, right? समझ में आ रहा है? Right?
हाँ सर, समझ में आ रहा है.
Okay, okay, right. हाँ. ऋतुजा कदम, समुद्री, समृद्धि.
Yes, sir.
हाँ.
समजतंय.
समजते का? बरं बरं.
Yes,
ठीक
sir.
आहे. तर काय करा, घरी पुस्तक वाचा आणि त्या खालती जे क्वेश्चन्स आहेत ना, ते थोडस विचारण्याचा प्रयत्न करा, जेणेकरून की वी कॅन डिस्कस दोज क्वेश्चन्स हियर, राईट? सो हियर just we are firstly brush up our basic concept, and then we'll go selectively, means objective questions. So I will try to correct some objective questions. So I will ask questions and will explain what is the answer of that one. Okay, and even though if you want to ask a question, you may ask, so that we can discuss first that one. Okay, then should we stop here? क्या लेना है आपको और? Yes. हाँ? और लेने का है?
हाँ, लो.
लेने का. Okay. So I have one lecture at 10 o'clock of MSc. Means I have to take their exam. Right? That's why I may not continue. Okay, you tell me any difficulty that I will take first. Any difficulty? No difficulty.
सर लैम्ब्डा मैक्स कैलकुलेट करना है ना? हाँ उसमें
हाँ, yes.
38 नंबर का पेज नंबर 82
हाँ, पेज नंबर 82.
उसमें
हाँ,
38
38. 38 ना?
हाँ
38.
हाँ
Not this one. Here is the pi bond. Here is the pi bond, and here is your compound. Same. Ankita, यही है ना? Yes.
yes
Okay. So
yes sir
here we have to see the basic value. Firstly, look here. It is your CO group: alpha carbon, beta carbon, gamma carbon, and delta carbon. Right? Basic
तीनों
value. It is a 6 number. So basic value कितना है? 215 nanometer. Okay. 215 nanometer. Number 2 क्या है? इसके अंदर extra double bond in the conjugation है क्या इसके अंदर?
कोकोएनुलर
Yes.
लाइन
Yes.
एक्स्ट्रा डबल वन
Extra double bond in the conjugation means you have to add 30 nanometer, right? Next one, हाँ बोलो. Ankita, yes, you tell me all. Extra double bond in the
होमोएनुलर
conjugation.
डाइन
Homoannular diamond.
होमोएनुलर डाइन
Right. 39 nanometer. 39 nanometer, right? And next one, yes.
अल्फा
Next one,
सब्स्टिट्यूएंट
alpha substituent. Look here. Also you have to see hexacyclic carbon-carbon double bond. Hexacyclic carbon-carbon double bond. Look here. The bond between the C alpha and C beta is hexo to this ring. Right? Means you have to add what? You have to add 5 nanometer. Right? You have to add 5 nanometer, and you have to next one. You have to go for the substituent. Add alpha. Add alpha. There is a one substituent, so means you have to add 10. Okay. Number 10 nanometer. Number next one. Add beta. There is no substituent. Gamma and delta. And again add delta. You are having a one substituent. Means you have to add 18 nanometer. 18 nanometer. Right. Just you have to add, and you will get the answer. इतना ही है. इसके अंदर इतना ही add करो. You get the answer. Right? हाँ.
पूछना
yes.
किया तो 317 आ रहा है और में वो 287 है, तो ये बराबर है ना अभी सॉल्व हुआ?
यही बराबर है. Right? So
वही पूछना था.
You go through it. What happened? There will be some printing mistake in your book also sometimes, right? Or due to some maybe in another reason, there may be some wrong in some reference book or in some any other book also, right? So it is a printing mistake, right? So you follow the rules and regulation, you get the correct answer. You get the correct answer. Apart from this, there is no need to add anything, right? So these are the things. Okay. So we'll in the next lecture we'll see the. Okay, tell me the sequence of the electronic excitation. Sigma to sigma star, right? Then N to sigma star. Then pi to pi star, and then N to pi star. Right? So this is a sequence. Sometimes they may, instead of giving 4, they may also give also 2, 3 also, and they ask arrange according to increasing and decreasing order. So remember this sequence. Of course, they'll ask one question on this one, right? Sigma to sigma star, N to pi star, pi to pi star, and N to pi star. They will ask the increasing or decreasing order of the electronic excitation. Okay, and as an orange point of view, here pi to pi star is important, and here N to sigma star. Here is N to sigma star, right? N to sigma star, right? So these are the some concept in the UV. Right? So it is 11:38, at 12 I have oral of MSc project runs. So I think here we should stop, right? Tomorrow in morning at 11:30 I have a lecture of that is the FYBSc. So what you can do, after that lecture you can take it. Okay, otherwise we have to start 11, I think it's 11:30 to 12. 11:30 to 12. So 11, up to 11:30 you can take, right? Okay, 10:30 to 11:30. Understand?
Okay.
Okay, then I think we should stop here. And if you are in doubt, you can ask. यदि आपको कोई डाउट है तो आप पूछ सकते हो, अदरवाइज विल स्टॉप हियर.
नो डाउट सर.
नो डाउट. समृद्धीचा अभ्यास करता घरी का?
ये सर चालू है.
Very good, बहुत बढ़िया. Right? You make a group of yourself and try to discuss this question, so it becomes easy to understand. ऑब्जेक्टिव्ह मध्ये पाठांतर करायचं नाही, ऑब्जेक्टिव्ह मध्ये समजून घ्यायचं. समजलं ना, फक्त त्यावेळेस फक्त आठवलं पाहिजे. मीन्स इट इज अ एग्जाम ऑफ युअर मेमरी. जिसका मेमोरी स्ट्रांग है, जिसका जल्दी याद रहेगा और उस समय याद आएगा, उसको ही अंक मिलते हैं, राइट? तो हम यहाँ पे कौन सा भी कंसेप्ट अपने को याद नहीं करना, राइट? उसको समझना है.